Welcome to Maths with EJD. Technically, I'm still continuing with with differential equations generally, but then I feel that for partial differential equations, I should create a different playlist. And just like what I did for Laplace transforms, I should also, in as much as this is a standalone playlist, I'll also add it to the general differential equations playlist. So people can have different options of, checking them out. So of course, as expected, this first video is about introduction to partial differential equations, PDEs for short. Okay, so let's start with an overview as usual. So a partial differential equation, I think I made mention of it at the initial stage of the differential equations playlist, but now we are going in depth into partial differential equations. So a partial differential equation, or PDE, is a type of equation that involves unknown multivariable. I think that's the key word here. Unknown multivariable, unknown multivariable functions. So a function with many variables and their partial derivatives and their partial derivatives. So many variables or partial derivatives in the sense that at any point in time you can talk about the derivative of one or more of the variables and their partial derivatives. Okay, so unlike ordinary differential equations, unlike ordinary differential equations, otherwise known as ODEs, which involve derivatives with respect to a single variable. PDEs capture changes across multiple variables. Okay, this makes PDEs, that is, this makes them particularly powerful, particularly particularly powerful for modeling systems where behavior depends on than one independent more than one independent factor, okay, such as space and time. So for whereas ODE can take care of only space, only time, or only space, PDEs can take care of both space and time, and even more. So, many things in reality actually depend on more than one variable. That's why PDEs are more realistic in modeling physical systems or natural systems, things we relate with from day to day. So, a very good example of ODE, like we've been seeing, is when the y dx is equal to y. So that means that this means that y is only a function of x. Okay. On the other hand, we can have PDE. PDE can now be partial u, partial t, okay, equals alpha partial squared u, partial x squared. So this is coming from the fact that, in this case now, you have u as the dependent variable. So it means u here is a function of both space and time. So it's a function of both x and t, or time and space, anyhow you like it. So you see one variable here, you have two variables that are independent, right? So you see here, the PDE here, the PDE represents the PDE you have up there actually represents heat diffusion. Heat diffusion. You know, when heat diffuses, it over time, it diffuses in space. So it depends on space and time. As time goes on, heat spreads from one source to another point. So here, the PDE represents heat diffusion over time and space. Okay, whereas ODE, whereas the ODE only captures change, only captures change with respect to one variable. So that's the deal with ODE and PDE. So PDEs are fundamental in describing phenomena in physics, engineering, biology, and even finance, including processes like fluid flow, heat conduction, wave propagation, and quantum mechanics. Okay, so we have all that. Okay, switching over and let's take this. Now, let's talk about classification of PDs. Classification of PDs. So how do we classify PDEs? Okay, so we see PDEs classified. Classified. PDEs are classified in several ways. First of all, we can have classification based on order. Classification based on order. So we say that the order of a PDE is determined by the highest derivative. It is determined by the highest derivative in the equation. Okay. So for instance, we have we have first order, first order PDE. So for first order PDE, this involves only first partial derivatives, only first partial derivatives. So an example of that would be this example. You have a of x comma y partial u partial x plus b of x comma y partial u partial y, and that is equal to c of x comma y. So in all, you see, first order, all the derivatives, I mean, the highest derivative we have is of first order. So that's a very good example of that. Then you can also have you have a second order. You have second order PDE. So for second order PDE, right? This involves second order derivatives. It doesn't mean that there won't be other order of derivatives, but the highest you have is the second order, okay? So a good example of this would be partial squared u partial x squared plus partial squared u partial y squared equals 0. So all the derivatives are of second order, but that is not the reason why it's a second order. It's a second order because the highest derivative is second order, right? So it means I can make up another example. Say I can make up something like, say, I have partial squared y, okay, partial x squared, say minus L. I mean, this is not any known equation. I'm just making this up. So, and then you have partial u, partial y, right? Y is the dependent variable. So partial y, partial t equals 0 or equals whatever. So because the highest derivative is of second order, so this is also an example of a second order differential equation. So this is example 1, this is example 2. So we can classify differential equations based on order, all right? So another way of classifying would be what we see next. Number 2, how do we classify partial differential equations? We can classify it based on whether it is linear or not, and that is talking about linearity. So for instance, linear, we have linear PDE, okay? So in this case, the dependent variable and its derivatives appear linearly, okay? They appear linearly, okay? So that means no, they don't have powers, and there are no products, no powers products, or non-linear non-linear functions. So meaning that the derivatives of order 1, I mean, the power of the derivatives will be order 1, it will be 1, and they are not multiplied by any other, uh, by the derivatives. So a very good example of that would be this example. You have partial u, partial t equals partial squared u, partial x squared. So you see so if a shorthand form of writing this would just be ut equals uxx. So you see that this u, if it now becomes u squared, it's no longer linear. Or if this becomes u squared, it's no longer linear. Or if I now have 1 over u of t, it's no longer linear, right? Or if I now have u times ut, it's no longer linear, okay? So but in this case, they are linear. So we have nonlinear PDE, nonlinear partial differential equation. So this actually contains a nonlinear PDE contains nonlinear terms, just like I demonstrated up there. It contains nonlinear terms. Okay. Um, for example, nonlinear terms, e.g., so nonlinear terms would be things like u multiplied by a derivative of u, or something like partial u, partial x now, all raised to power 2. These are all nonlinear terms, okay? So a very good example of that. So anywhere you see the dependent variable multiplied by another, its derivative, or has power more than 1, or any of the derivatives has power more than 1, has degree more than 1, just like we saw for ODE, then you know that's what we say, then we say it's nonlinear. So here we have partial u, partial t plus u partial x equals 0. So this makes it nonlinear. Or maybe you now have partial u partial x squared plus partial u partial y equals whatever. Maybe equals, say, yeah, equals 0, even whatever that is. So this now makes it nonlinear. Okay, so you have nonlinear PDEs. So another way of classifying PDEs would be according to the type. Okay, type. So uh, we talk about type for second order linear PDEs. So types come to play for second order linear PDEs. And this is really important. So let's see what the classifications look like here. So the classification into the classification into elliptic. So you can have ODEs that are elliptic if they have second order. They can be parabolic. It can be elliptic, it can be parabolic and hyperbolic, right? So the classification into elliptic, parabolic, and hyperbolic comes from the nature, of their solutions. So they are all of these things because of the nature of their solutions and their resemblance and their resemblance and the nature of their solutions, right? And their resemblance and their resemblance and their resemblance to conic sections. I've not done geometry so far. Maybe we'll get to talk about that along the line. So conic sections talk about ellipses, parabolas, and ellipses, parabolas, and hyperbolas. Okay, and so the solutions to these these partial differential equations resemble these conic sections. All right, and that's why we can say they are elliptic, parabolic, or hyperbolic. So, and their resemblance to conic sections. All right. So for a general second second order PDE in two variables, generally, right? So we have a partial squared u partial x squared plus 2b partial squared u partial x partial y, then plus c partial squared u partial y squared plus any other term that comes that are different from this, whatever, and that is equal to 0. So if we have this general form, right? So if we have this, we can classify. So we classify based on the discriminant. You remember the idea of discriminant, it comes up under when we talk about quadratic equations, right? We classify based on the I said discriminant, based on the discriminant. And what is that discriminant? It is simply D equals B squared minus AC. So for quadratic equation, that will be D equals B squared minus 4AC. But for partial differential equation, it is D equals B squared minus AC. So based on this now, we can have types of parabola. First of all, we have the one that is elliptic. So the parabola is elliptic if D is less than 0. So an example of that is the Laplace's equation. Laplace's equation. Okay. So a good example would be the Laplace's equation. Then we have a differential equation. Partial differential equation is parabolic if D is equal to 0. Okay. That if you evaluate this now, if you take B from here, this B, B squared minus A times C, if you do it and you get D, if the D is less than 0, then you say that's Laplace equation. It is parabolic if that D, when you evaluate it, it is equal to 0, you say it is parabolic, and that happens for, say, heat equation, all right? And we also have it to be hyperbolic. It's possible that it is hyperbolic. It's hyperbolic if D is greater than 0, and in that case, we have something for wave equation. Okay. So Laplace equation is elliptic because D is less than 0. Heat equation is parabolic because D is 0. And wave equation is hyperbolic because D is greater than 0. Okay. All right. So let's look at some physical examples. At this point, we switch over again where this comes here, and then maybe we go for this. Okay. So physical examples. Of course, I've mentioned those physical examples up there. Physical examples of PDEs. So all those equations I mentioned are actually the physical example. Here, we want to talk in a bit more detail of them about them. So we have heat equation, just like you've seen up there. So heat equation, it's generally given as partial U partial T equals alpha partial squared U partial X squared. So part of what we'll be doing under this playlist is to solve some of these equations. So what does the heat equation do? It models heat heat diffusion in a rod, over time. So if you hit a rod at one edge or in the middle or at any point, the heat spreads within the length of the rod as time goes on, and within the length of the rod, that's space. Over time, that's time, right? So then we say it is parabolic PDE, parabolic PDE. Now, what makes it parabolic? So you see the heat equation, if you write it in the standard form, right? If you write it in the standard form we saw up there, what's that standard form now? We have a d squared u dx squared. So this is so a d squared u, there's d squared u dx squared, right? So if we can have it as alpha d squared u dx squared. Okay. So what do we have next? We have d squared u dx dy. We don't have that. So this is x and t. So we can have plus 0, all right, plus 0 d squared u dx dy because we don't have anything. That'll be dx dt because this is x and t. Dx dt. So that is 0 because we don't have that. The next thing is d squared u dy squared. Okay, d squared u dy squared. Here we don't have d squared u dy squared, or we don't have d squared u dt squared. So that will also be 0 d squared u dt squared. Then we now have du dt. So if you transfer everything to the left hand side, to the right hand side, so this will now be minus partial u partial t, and all of that is equal to 0. So you see, a is alpha, b is 0, c is also 0. So if you now do d equals b squared minus 4ac, right? So that is d equals b squared as 0 squared minus 4 times a. A is alpha, c is 0. So d is simply 0 minus 0. So d is 0. And when d is 0, what do we get? We say it's parabolic, okay? So it's simply parabolic because d is equal to 0. So that's why the heat equation is a parabolic partial differential equation. Okay, so it's parabolic. So what's another point for about the heat equation? And another thing here is that it is u of x comma t represents, so u itself represents temperature. So u represents temperature. Okay, because it's heat equation, right? Then alpha is thermal diffusivity. Thermal diffusivity. So it's an index for how heat spreads within the rod. So, and that will depend on the nature of the rod. Okay, so what is the application of the heat equation? We can see, because it's heat equation, right? It's useful for cooling of metal rods, cooling of metal rods. Maybe in industries, maybe steel industry or wherever. Then temperature distribution in materials, temperature distribution, temperature distribution in materials. Okay, so these are some applications. All right, so we go for the second one, which is the wave equation. Okay, these are popular partial differential equations. So we have the wave equation. So when you talk about the wave equation, okay, so it's given as partial squared u partial t squared equals c squared partial squared u partial x squared. Okay, so what does it do? First of all, it models vibrations, it models sound, light. Sound is a wave. Light can also be a wave because we have the wave particle duality of light. Or we can also have water waves. When you talk about ripples in waters, in water bodies or something. So we have water waves. Then the next thing is that it is hyperbolic. It's a hyperbolic PDE. Hyperbolic PDE. So if it's hyperbolic, if the discriminant b squared minus 4ac is greater than zero. So can we confirm that? So if you arrange this according to what we have up there, if we start with we have x and y, right? Let's assume x is x and we now take t as y. So if you write that out, we have c squared partial squared u partial x squared. Then next we don't have partial squared u partial x partial y. So that will be 0 partial squared u, then partial x partial t. Then we have for the other one a partial squared u partial t squared. We have it here. So this is so if you transfer it to the other side, right? If you transfer it here, okay, so that means we have minus partial squared u partial t squared equals 0. That's all we have. So now this is A, this is B, and this is C. So C is minus 1, as you can see. So that means that D is equal to B squared minus 4AC. And that is, what is B squared? That's 0 squared minus, oh, no, not minus 4AC. I am thinking, I have brought in the idea of partial different. Hope I've not done it. I didn't do it. Okay. Yeah. Oh, I made a mistake here. So it's not minus 4AC. It's AC, sorry. It's AC. So yeah, it's AC. Thankfully, that will be 0. So that we are good. So 0 squared minus AC. A is C squared. And what is C? C is minus 1. Okay. Interestingly, D now is equal to 0. Minus and minus is plus. So we have plus C squared. So D is equal to C squared. And C squared is greater than 0. So it means D itself is greater than 0. And when D is greater than 0, we say it is hyperbolic. D is greater than 0. That's hyperbolic. All right. So that's why the wave equation is hyperbolic in nature. So we continue and we talk about the wave. In talking about the wave equation, still we have C. C is the wave speed. So C is the wave speed. So how far does the wave travel? It depends on the medium we are looking at. So C here is the wave speed. So then let's talk about some application of the wave equation. Application. Okay. So we have it in vibrating strings, like when you strum your guitar, violin, or other stringed instruments, vibrating strings. Then we have it in seismic waves. Okay, like we talk about shock waves associated with earthquakes. Then we have electromagnetic propagation, electromagnetic propagation. Okay, so maybe in propagation, maybe in telecommunications and things like that. Okay. All right. So we also go on to talk about the third type, another physical, very popular equation, partial differential equation. That is the Laplace's equation. Laplace's equation. So for the Laplace's equation now, what do we get? So that is partial squared u, partial x squared plus partial squared u, partial y squared equals 0. Okay, so this actually describes, so it describes steady state solutions with no change over time. Okay, steady state solution with no change over time. Then it is an elliptic PD, elliptic partial differential equation. What makes it elliptic? The way to know that is to check to write it in the standard form, where we have a d squared u dx squared plus 2b d squared u dx dy plus c d squared u dy squared. Okay, so it's almost in that shape, except that we just need to insert the dx dy part. So we have partial squared. Let me start from the top so I can have a bit of space to do what I have to do. Partial squared u partial x squared plus 0 partial squared u partial x partial y plus partial squared u partial y squared equals 0. So it means A is 1, B is 0, and C is also 1. Okay, because the coefficient is just 1. So we now have the discriminant d equals b minus a b squared minus ac, not 4ac, please. So b squared, that's 0 squared minus a is 1, c is also 1. Okay, so we have d now to be 0 minus 1, which is minus 1. So d is less than 0. And when d is less than 0, that is automatically elliptic in nature, just like what we have here. Okay, so elliptic, d is less than 0. So it means that a Laplace equation is elliptic. So we go on to talk about other things as far as Laplace equation is concerned. So let's look at the application. So interestingly here, we don't have any constant like thermal diffusivity or heat equation or wave speed for wave equation. So the application, you have application in electrostatics, with based on what it measures, right? It describes steady state solutions with no change over time. So electrostatics, so you see some static stuff there, static electricity, then fluid flow. Fluid flow is another one here. Fluid flow, fluid flow, fluid flow. Okay. Then we also have gravitational potential fields. Gravitational potential fields. Okay, so these are examples. So I mean, in conclusion, right, these PDEs form the foundation for mathematical modeling in science and engineering. They reveal how physical systems evolve and interact, guiding us from theoretical formulation to practical solutions through analytical or numerical methods. Okay. Should I write that? Yeah, I think I've said it. I think that suffices. So be sure to let me know in the comment section how helpful this video is for you and other videos you see in this channel. Go ahead and let me know. And of course, let me also know. Okay, let me see if we can get practical questions. Can we get practical questions? I'm not sure. Let me see the nature of practical questions we can have for this, if any. So you can try your hands probably to identify the types of PDE and things like that. Okay. Uh, okay, maybe I should just give just this simple one. Practice. Okay. Of course, you want to test how does a partial differential equation differ from an ordinary differential equation in modeling temperature across a metal plate and all that. Okay. Which PD would you use to model the vibration of a guitar string and why? You may also think about that. So, but let me give only this one. The PDE, given the PD partial squared U partial x squared equals 4 partial squared U partial y squared. Okay. So classify it as elliptic, parabolic, or hyperbolic. Of course, you know what to do. Arrange it in the standard form and check for the discriminant d equals b squared minus ac. And then you can tell if it is elliptic, that's when d is less than 0, parabolic when d is equal to 0, and hyperbolic when d is greater than 0 easily. So let me see your answer in the comment section, either on YouTube or on Facebook. And like I said, let me know how helpful these videos are for you. And if there's a problem you'd like me to solve or a topic you'd like me to teach on, I'm able to find time along the line to do all of that. And if you have subscribed to this channel, thank you for that. For those who have not subscribed, please go ahead and subscribe because there's a lot for you to learn on this channel. All right. And of course, don't forget everybody to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.